You never accidentally put the car into huge oversteer. You're never getting a feeling where the pedal feels like nothing and then all of a sudden there's too much. The regen blends in really nicely. So like all of that sort of thing, you can really get a lot of enjoyment out of, but the challenge of developing the torque in the first place isn't there anymore. That part's really easy.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Sasha Anis. Sasha is a long-time friend of High Performance Academy. He's joining us from his home in Canada. And Sasha, over the years, has been involved in owning and running On Point Dyno, a mobile dyno tuning facility. He's more recently, though, moved into the electric vehicle world, and specifically, he runs Mountain Pass Performance, which make all manner of suspension brake upgrades for the Tesla brand. Now, Sasha was an early adopter of electric vehicles, and many years ago he converted a Lotus Evora to use a Tesla drive unit. So he's no stranger to EV performance, and he's dived deeper than most into what makes an electric vehicle tick. These days, unless you're hiding under a rock, it's no surprise that electric vehicles are becoming more and more prominent. And while I don't think we're in danger immediately of seeing internal combustion engines fade into obscurity. I'm pretty confident they're going to be around for a while to come. We are seeing more and more EVs come out. There's some really exciting technologies involved, and naturally, as people start crashing production electric vehicles, we're seeing more and more of these come up available for really attractive price points at the wrecking yard. So this really begs the question, is an electric vehicle conversion viable? Well, we're here to talk with Sasha about what actually goes into electric vehicle conversion, what the actual parts of the EV system are, and most importantly, how we make them all talk to each other. Now, as well as his forays into electric vehicles, Sasha is also really well known for his time attack Nissan 350Z. It's powered by the 350Z V6 engine, albeit one that's producing a lot more power than stock. However, he has essentially blended together his passion for internal combustion and electric vehicles and added essentially a KERS system to his 350Z. So we dive into that as well. That, to be honest, is a complex system. Really, really interesting though. We find out from Sasha exactly how all that works. A really interesting interview and a lot of great takeaways for those who are maybe interested in what's coming up in the aftermarket when it comes to electric vehicles. For those who are new to the podcast and maybe haven't heard of High Performance Academy before, just a quick intro. We are an online training school. We specialize in teaching people basically anything that you'd want to know about the performance automotive industry. This includes engine tuning. We also cover engine building, wiring, which cover driver education, data analysis, and race car setup. As I mentioned, all of our courses are available at hpacademy.com/courses. And while it's a little bit of a stretch, because we did talk to Sasha today about his 350Z, which, as I mentioned, does still incorporate an internal combustion engine. If you are interested in learning about EFI tuning, then our EFI tuning courses will be perfect for you. I'd suggest checking out our EFI Tuning Fundamentals course. As its name implies, we'll teach you the fundamentals of EFI tuning applicable to absolutely any engine and any engine management system. If you are interested in learning how to tune an aftermarket standalone, in the case of Sasha, he's running a Motec, but again, this course is generic. It will work with any ECU you may be personally interested in. I'd suggest you check out our practical standalone tuning course. That teaches you how to tune an aftermarket standalone ECU. Now, we know that when it comes to tuning your very first engine, particularly if you've got a freshly installed ECU with no base map, it can be really daunting. What do you do first and what order should you progress in? Well, this course breaks the entire process down into the HPA 10-step process. By doing this, each of those individual steps is relatively quick and easy to complete. In no time, you've got to the end. You've got a completely tuned engine that's delivering great power, great torque, great drivability, and most importantly, great reliability. Now, if you are interested in learning more, again, we'll put a link to the show notes for both of those courses. And if you are a podcast listener, you can use the coupon code podcast75. That's going to get you $75 off the purchase of your very first course. All right, enough with our intro. Let's get into our interview now. All right, welcome to the podcast, Sasha. Thanks for joining us today. You, from what I know of you, you're a long-term internal combustion fanatic. You've run a dyno performance workshop. However, you were also at the forefront of moving into the EV sort of era, particularly with a very well-known Lotus that you built. And we're going to talk about that. I'm also going to talk about the 350Z that you're really well known for a little bit later on, because there's some EV technology you've managed to sort of graft into that. What I'm interested to start with is learning about your early adoption of electric vehicle technology. A lot of us, particularly those who have been around internal combustion engines for a long time, we don't like to change our ways, and moving down to EVs is a very big shift in mentality. So what made you embrace that so quickly?
Oh, well, first of all, thanks for having me. It was a few years ago now, so I don't really remember what the main catalyst was, but part of it was the interest in learning about the technology. Teslas were starting to come out at that time and had a good bit of power, and you're like, wow, like, okay, like how long can you really run these things? What's involved? And start doing some research and getting more and more interested, more for the road car applications too. It's like, it'd be really great if we could have exciting to drive cars that you drive day to day that aren't burning fuel and, don't have all these other long-term issues. So there was some of that as well. I kind of started to feel a little bit just not quite right with dyno tuning every day and just reading in the news all this stuff about climate change all the time. So I don't want to be that guy preaching, but that was definitely part of it.
Yeah, I think that's fair. I mean, we do work in an industry that's really at odds with the climate, and I mean, I'm not here, as you've just mentioned, to preach that aspect, but I don't think there'd be too many people that are going to disagree that there's definitely some big advantages with getting away from burning fossil fuels. So we look all around these days. Obviously, the Lotus that you built, we'll talk about more in detail. As you mentioned, it's a few years ago now, but these days you've got to be living under a rock if you don't think that EVs are the way that we're going for the future. So whether you like it or not, that's what is going to happen, and it is an exciting technology that I'm certainly looking forward to seeing how it develops in the aftermarket, and looking forward to jumping in and embracing it. So maybe let's just take a step back before we build further into the sort of EV world that you're now very heavily involved with. And I'm interested to learn how you got involved in cars in general, and particularly you are known for tuning. So that's, as we all know, is a very difficult industry to sort of build a reputation in. So can you tell us how that all sort of came about for you?
Yeah, I mean, I don't want to make it a long story, but I got into cars through my passion for racing. So it started off as, I think a lot of people that run shops, you build a car for yourself and you run it in a local racing series, and then you say, oh, I like this, so I'm going to try and do it for a living. So after 5 years or so of running a race shop, and we won a few championships and had good success, but as I think a lot of race shop owners know, it's a grind, it's really difficult. So I tuned my own cars. Thankfully, I had a friend who owned a dyno, and he had a mobile dyno tuning business, but his business was more to rent the dyno out and someone else would do the tuning. So I learned how to tune using his dyno on my own race car, and just started offering those services while I had the race shop over those years, and it turned into closing the shop and running just a mobile dyno tuning business full time. And that worked well. We supported a number of pretty cool cars over the years, and I really enjoyed the electronics, the control aspect, and learning and thinking about all the different things you could do. Electronics are really powerful when you learn about them, and how, especially when you look at professional motorsport race cars out there, how much lap time you get from those types of things like traction control and ABS. There's a lot.
Yeah, I think that's something that's very easy to overlook, and particularly the advances we've seen in the aftermarket electronics we've got available to us just even over the last decade that I've been in the industry. That they've really come so far, making it so much easier for us to extract performance out of cars.
Totally, and reliability as well. And so, and And that goes in line with the data logging and looking at data. I mean, when you're tuning cars every day, you're just looking at data logs constantly. So all of that kind of just built up this interest in electronics. And I think that's kind of one of the reasons we moved more in that direction. You're familiar obviously with M1 build. So then I started getting more comfortable with M1 build, and then that and the Lotus kind of came together. I said, I bet I can do something pretty cool with M1 build with an EV swap.
Let's just pause there for a moment for those who maybe aren't sort of well versed in the Motec sort of language. So M1 build, that's a Motec product for the M1 range of ECUs, and you are, of course, Motec Canada. So you're fairly heavily focused on the Motec range of products. So for those who aren't familiar, can you talk us through maybe how M1 works in terms of firmware, and then how M1 build works if you want to make something that's not available?
Yeah, and I don't mean to shamelessly self-promote here, but the concept is basically that you can get generic firmwares for an M1 ECU that do different things. So they group together functionality, whether you want a road car or a car that's got traction control and launch control, and you get different versions, and those are called packages. But what M1 Build allows you to do is it allows you to do custom programming and program in your own functions and features, however you can imagine them. But it allows you to do so in a way that, I mean, I had played with Arduinos. I had done a little bit of coding learning. I wasn't a programmer at that point. But M1 Build allows you to get in at this much higher level where all that low level signal processing and really complicated code is handled for you. So you can focus more on the logic and organizing your control strategy the way you want. And it was really, I would say it was really empowering. And that, I think, really, to be fair, catapulted the EV project, because if I had to write all that code in low level on like an STM32, I mean, I would never be able to do that.
Yeah, and it segues nicely into your sort of EV build, obviously giving you that flexibility to make the firmware do essentially whatever it is you want to do. I don't want to get off too off topic here, but just while we are talking about M1 build, and it's a topic that has come up over a few episodes in the past, but for me, and I've gone a little bit down this path, I've programmed some functionality that I wanted. I had my own flex fuel package essentially before Motec had one, because I wanted to. I just wanted to see how it worked. But the skill set, where I was going with this, the skill set sort of required to write code in M1 build is quite different to that skill set required to tune an engine. So how did you build up that knowledge? And I guess the other question that comes off the back of that is this a skill set that you think an average tuner can develop?
I was not a programmer. So, I was almost embarrassed at my level of programming ability at that time. So absolutely anyone can learn how to do that. I mean, I always like to compare that every human being knows how to run and walk, and that's pretty complicated. I mean, to get someone with a center of gravity that high to be able to stand and not fall over is pretty complicated. So your brain is pretty powerful. You just have to have the willpower. And if you say you can't do it, it's probably just because you're a bit lazy or not that motivated, or it doesn't matter to you that much. That brings me into the point of M1 build and programming in general. Unless you're going to be focusing on that and selling those services to other businesses, it's not necessarily a very profitable, there's not many people that are going to pay you to spend weeks and weeks programming custom firmware into an ECU that already does everything really, really well. You have to be offering your services to a specific niche. But how I learned M1 build was I looked through the code that was there in the sample projects, and I tried to understand. I mean, it's fairly legible in English. There's not a lot of complicated syntax, and just change one little thing and upload it to the ECU and see what happens. And then you get comfortable and you do one more little thing, and it was like those little baby steps, until you got to a point where you could do more or less whatever you needed to do. But it definitely didn't happen overnight.
I think that mirrors my own experience, and I mean, I definitely haven't gone as deep down the rabbit hole as you have. Unfortunately, I just don't have the time these days to devote to all of the elements that I'd like to sort of dive into in as much detail as I could, and M1 Build is one of those. But yeah, I just for a bit of background, when I was at university, I actually started on an information engineering degree, and very quickly at that point found out that programming just did not gel well in my head. So I actually changed my major for that degree and went into product development. So yeah, that gives a basis of at that time it was literally a foreign language to me, and I think necessity is the mother of invention, as they say. When I came back to this years later. And now all of a sudden I had a problem that I wanted to solve. I wanted flex fuel, and Motec couldn't provide it. Yep. And be damned if I wasn't going to figure that out for myself. So
I'm 100% the same. Yeah, I got 50% in French in high school. I have a horrible memory, and trust me, I was exactly the same trying to learn programming. But like you said, as soon as I wanted to figure something out for real, it all of a sudden the door opened and started making progress. So we're the type of people that it has to have a practical application, and
definitely,
no better practical application than something for a race car. So
I think that's the same with I was about as good as you by the sounds of it at foreign languages at school, and I think the only way I was ever going to get any good at that was total immersion, where if I couldn't speak the language I wasn't going to get fed. So right. That necessity is a really important part there. And I will also add here, I do have a friend who codes for a living who was quite helpful, and I'm very embarrassed anytime I had to actually show him the code.
Sure.
I mean, I got from A to B, but it was probably via the most convoluted and nonsensical path possible, but I got the result.
To be fair, I mean, before we leave the programming subject, I have worked with a number of programmers, and the value that people like you and I have is, we're not necessarily the most efficient programmers, or we don't understand the most efficient way to write code. But most programmers, not most, I should say, a lot of programmers don't have an intricate understanding of the application and the logic that you're trying to deploy. And just knowing exactly how you want the system to function and what to do when, that's really, really important. And I think people underrate that.
I couldn't agree more. I don't see this as much these days, but I've been in the tuning industry for 20 odd years now, and I've seen a lot of different ECUs. Particularly in the early days, I saw a couple of ECUs that I dealt with quite closely, and I won't name names, but they got the job done and you could tune an engine with them, but it was very clear, and particularly when you talk to those involved with coding, you had people who were software engineers or coders who had absolutely zero interest or passion when it came to cars or motorsport. And you kind of got a feature that was written from the coder's perspective without that deeper knowledge of like how that was actually going to work when it was employed. And you kind of just got a system that worked, but
kind of, not quite,
kind of.
Exactly.
I mean, I think that's kind of like comes back to the old story of feature list shopping when it comes to ECU. So XYZ ECU has traction control, and so does ABC ECU. Well, just because it has a line there that says traction control, I can 100% guarantee you there is traction control and then there is traction control. And what works for a motorsport application versus what will simply stop the wheels from spinning are two very separate things. Anyway, I think we've got a little off tangent here, although I think there's some value in what we just discussed, but we'll get back on track here with our EV discussion. And let's start with Blue Lightning, which is your Lotus Evora. And as we talked about before we started recording here, you said this has sat under a cover for the last few years. So things have moved on a bit for you. So we're sort of maybe scratching back into the sort of the deep past here, and maybe you're not 100% up to speed with everything you did back then. But can you give us like a high level view of what that car was and what you put into it?
It still exists. It was a Lotus Evora, so that's, if you're not familiar with Lotuses, that is Lotus's GT3 911 type car. It's not the small Elise, and Tesla made a Roadster based on that smaller body. So this Lotus Evora is kind of a bigger body, and we put it has a Toyota Camry engine, so we didn't feel too badly getting rid of that. And we put in a Tesla Model S rear drive unit, which at that time, there were very few people installing Tesla drive units, and getting someone that could control it was not so easy. So that was the main challenge. We use Chevrolet Volt batteries, which are great batteries. They have been used in many swaps, but they're a great battery that can support a ton of power for their energy level. So they're just a very power dense cell where now, and we'll talk about that more later, I suppose, batteries have gone more in the high energy direction at the expense of the battery potential. So
I'll stop you there, Sasha. Just with the choice of the Chevy Volt batteries, is this because the donor Tesla had no battery pack or the batteries were damaged, or was there an advantage as you saw it using the Chevy Volt batteries over Tesla?
Oh, yes, for sure. The Tesla batteries are in that category of very energy dense and very low power density. So effectively, to have the power output we wanted, we first of all wouldn't have the physical space, and we would add double the weight in battery that we added with the Chevrolet Volt batteries. We would have had much more energy and range, but the goal of the car was to keep it lightweight and high power.
Okay, so let's just clear up. You've used energy density as a term, you've used power density as a term, and those listening might consider those terms to be one and the same. Clearly, the way you're using them, they're not. Can you dive a little bit deeper and just explain the difference?
Yes. So basically, a battery, the chemistry of batteries, and I'm not a super expert on why this is, but you can have the chemistry of a battery to have higher energy density, but that means when you try to draw a lot of power out of that cell, it has a larger voltage sag. So in other words, the voltage drops when you put it under a lot of load. And once you put a battery under too much load and the voltage sags too much, you can start damaging the battery and you drop below the safe voltage. So basically what that means is to support the power you need to have more batteries so that each individual cell is under less load. So for a very energy dense battery, typically they have more voltage sag, cannot support as much power, and therefore you need more of them and more weight and more space to be able to have the same amount of power. The Chevrolet Volt battery, it was from a hybrid application. So it was always a very small battery, and it was designed to be able to drive without the gas engine running. So it had to be a high power, it had to be able to support driving the car at highway speeds, even out of a very small battery.
So high power density, lower energy density. So basically what you're saying here, just putting all that together as well, is the Chevy Volt battery would have not have been a good solution for high sort of mileage running. Is that correct?
Yes, exactly. I mean, if you wanted to put the same equivalent energy in terms of Chevrolet Volt batteries, you would now have, twice the weight almost of a Tesla battery. So if you want lots of power, you're going to have less energy. And if you want lots of energy, you're going to have less power. So pick what you want.
Okay. I think that's really important because that would be something I definitely haven't considered. And I'll be very frank here that I am very fresh to EV technology, so I don't claim to be an expert. That's why we've got you on the podcast. But I think just like myself, a lot of people would completely overlook that the battery has to be chosen to suit a specific application, and clearly those are very different.
And it's evolving all the time. We're getting now batteries coming out that are higher power and have still the same or very similar energy density. So it's always changing. And so I don't want to set these rules in place, but at the time then and even up till now, that is the state of the art, which is basically you have an energy cell and you have a power cell, and you pick what you want.
All right, so we've got this Tesla drive unit, we've got the Chevy Volt batteries, and what else is involved in actually making this all work together?
Yeah, I mean, there's a few different ways you can do it. I mean, you can do it simply so that when you flip a few switches and you retain the factory Tesla pedal, and the Tesla drive unit thinks it's still in a Tesla, and it drives the way a Tesla drives. That's like the very basic EV conversion route, which is quite common, but I really wanted to fully integrate it with the car. I wanted to add some features. I wanted to have full control of the torque, the regen, and then I wanted to also really nicely integrate other features like the cooling system and the charger, and be able to have high power level 3 charging. So all of that stuff ended up being the big project, which was doing the wiring design, doing the firmware, and adding these other modules such as a charger. because if the batteries are there in the motor, that's great, but you need to be able to charge it. So you need a charger. You need a DC-DC converter, which is effectively like an alternator. It basically takes power from the high voltage battery and then it converts it to 12 volts, 14 volts to charge and keep the rest of the 12 volt system running. And then you've got a complicated cooling system you have to think through because, all these components run at different temperatures. Batteries like to be as cool as possible in terms of performance. You're always trying to cool them down to, ideally, you want the water temperature to be 20 degrees Celsius or 15 degrees Celsius. So you have to think about how you want to mix everything together. You have a motor where the output water temperature might be 60 degrees Celsius. So, it's not so straightforward always. It's not just one coolant temperature all the time. So in this case, we did a loop where the motor connected to the heater core, so it could, in cooler weather, you could get some heat from the motor to warm the cabin. And then we had some different valves and bypasses so that we could play a little bit or pick and try and prioritize how we're cooling and heating the system. So that we put some thought into that as well. And the Motec had some authority in controlling those systems.
I'll stop you here, Sasha, because you've just listed about 100 things that I want to sort of dive into a bit more detail before I lose my train of thought on it. The cooling system is interesting because, so we'll focus on that just briefly. I think because a lot of people kind of think, okay, obviously internal combustion engine, we have a radiator, the engine creates heat, we need to get rid of the heat, and generally most production engines are probably somewhere in the region of about 30% efficient. So it's producing a huge amount of heat that we need to get rid of. And I think, again, those with no previous understanding of electric vehicles would assume that cooling isn't really a factor. So you've mentioned the battery packs, you've mentioned the electric motor itself, and we need to cool both elements. And is that the same cooling path through the batteries and the motor, or are you running separate cooling systems for each?
Yes, exactly. So the key difference is that you need to shed a lot less heat with an electric vehicle, but because you're doing it at such a low temperature, your difference between ambient and the temperature in the radiator is much smaller. So it's still a challenge because you want the water going through the battery to be pretty much ambient. So you're never going to get enough cooling, especially if it's a really hot day, for maximum performance to stop that battery from overheating. So it's not so much that the battery is getting so hot. I mean, it's shedding obviously way less heat than the internal combustion platform is, but when you can't shed the heat at 100 degrees Celsius, it's just a lot harder. So in the Lotus, we have it basically where we do have the two systems together, but we can isolate the drive unit through the heater core when we want. The setup worked decently for us, but still, it's a Tesla Model S drive unit, and the drive unit will actually end up overheating before the battery, because at the time, that's as good as that inverter and motor could be. It would overheat still after only 4 or 5 minutes. Interestingly, it wasn't even the temperature of the coolant that was the problem. It's just the internal components aren't connected well enough to the coolant to be able to dissipate their heat.
So basically the coolant couldn't actually get rid of the heat that's being generated, is what you're saying.
Right, and it's an induction motor, and in that type of motor, a lot of heat is created that is just very difficult to get rid of.
Okay.
Yeah, but on to kind of just expand on that, on newer applications, the battery loop and the motor loop is often able to be separated or run in parallel at different temperatures.
Okay. You mentioned that 4 or 5 minutes and the motor would overheat. So I assume if left unchecked, ultimately that's going to result in damage. So I'm guessing there's some control strategy comes in here as a sort of a case of then it starts to derate the torque output in order to maintain or control that temperature.
Yes, exactly. I mean, unlike an internal combustion engine where you've got one coolant temperature sensor, I mean, an inverter has multiple different temperature sensors on every phase. It has multiple different sensors inside the motor. So it is able to really, really carefully monitor itself and prevent itself from damage. In the case of the Lotus, we're still using the Tesla control unit in the drive unit. So it still has the factory limitation for the power when it's overheating. We did add additional tables in the firmware to be able to proactively handle that. So for example, if I know I want to run for longer, we'll lower the power, and based on temperature, we can stop any regen. So we can prevent it from producing more heat so we can run for longer at the sacrifice of draining the battery a bit quicker. So
Sure.
It's cool. You can do all kinds of different things, but ultimately, yeah, you could probably bump it a bit from what Tesla was doing, but it would only get you another few seconds. Maybe it would get you another 30 seconds before it would really be too hot. So we're not talking about like, okay, I'm just going to turn all the limits off and just run it. I mean, you're going to be in big trouble if you just leave it unchecked. So absolutely.
Those safety strategies are there from Tesla for a very good reason, essentially.
For a reason, yes, exactly.
Okay, that's probably dealt sufficiently with the cooling there. So the actual control, you sort of already mentioned that you've got the Motec in there sort of interfacing with the vehicle electronics as well as the Tesla control unit. You also mentioned that a lot of people were swapping these and basically fooling the Tesla electronics into thinking that it was still in a Tesla. Now, I'll just kind of bring this back to conventional internal combustion engine technology. I mean, we've got some pretty sophisticated electronics in modern vehicles with multiple control modules all talking together across a CAN bus, for example, and it can be quite tricky, for example, then to remove the engine and the ECU for that internal combustion engine, put it in a different car and get everything running, because it may be requiring signals from other modules that will no longer exist. Is that the sort of situation you have to work around if you want to go down that Tesla drive unit swap and have it think it's still at home? And what solutions are there for that?
Yes, yeah, that's exactly what we did. And a good friend of mine in Switzerland helped with that. And he was nice enough to help me implement all of that into the Motec natively. And as a result, we have the ability to send wheel speeds and all these things from the actual car, not just fake signals, and really integrate it nicely. That was the method that we went. There's now also, I think AEM has a board where for that drive unit, you can just replace it. And it has now control of the motor, and it's its own CAN system. So I am not familiar with how that one works, but there's also a few other guys that have more of like an open source solution where they're directly controlling that older Tesla large drive unit. And I don't have any experience with that, with those ones, but I like the Tesla board because you have, well, no one's going to control the motor as well as Tesla, first of all. And the smoothness, I think it's going to be very hard to match. And then the power, like I said about the power limitations, I mean, that's really the only downside, and you kind of have to limit it anyway.
So you actually really could get yourself into a lot of trouble if you got rid of that Tesla control module itself.
Well, I know a lot of guys blew up inverters and motors like playing with them and learning with those open source boards. And I'm sure they learned a ton and it's awesome. But I thought for myself, especially learning early on, it didn't make sense to take unnecessary risk on that.
Yeah, no, that's fair. All right, so we've talked about a lot just involved with the Lotus project, and I'm sure you learned a lot as you went through this. And again, just for our listeners, this Evora was built a number of years ago, so of course the EV landscape is changing quite quickly as technology has advanced, and I have no doubt that the latest offerings from the likes of Tesla are probably far and away ahead of what you had available back then. What I'd like to get from you, and I mean you have already talked about some of these elements, but just to sort of get it all in a nice little package and tie a bow around it, could you run us through the components that make up an EV in general, sort of all of the electronics as well as the actual motor element, so we know what goes into an electric vehicle?
Yeah, sure. I mean, from the basic starting point, you have the motor, and it's some kind of gear reduction that connects to the wheels. And then you have an inverter, which is sometimes packaged with the motor, and that takes the DC voltage from the battery and converts it into the three-phase electric currents that the motor needs to be able to spin. So that's the engine and the transmission, basically. Then you have the battery, and you can kind of look at the battery as the fuel tank, I guess. The battery is usually the most expensive part, the most complicated part, the most difficult in an EV conversion to work with. The battery needs to be managed. So you have a power distribution box that connects the battery connects this power distribution box, and there you have fuses, and you have really high current switches, which are called contactors, and they basically disconnect the battery from the rest of the high voltage components. And in addition to the motor and the inverter, The other high voltage components you have are the DC-DC converter that we talked about, which is basically the alternator. You have the onboard charger, which takes power from your house's AC and converts it to DC to charge the battery. And you might have a high voltage air conditioning system, or you might have a connection to a level 3 high power charging port if you're doing a high level conversion, or an EV car would have that. Then you have the electric control units. So the electronic control units would be the battery management system, and that is usually packaged with the battery. It monitors each individual cell on the battery and works with another electronic control unit called the vehicle control unit. And the vehicle control unit is kind of more in charge of doing the torque requests, taking care of the cooling system, talking to the other components like the DC-DC converter and maybe the body control module and other, non-high voltage related systems in the car. And that's kind of like the master controller of making everything work, kind of like the ECU of an engine. And whereas the BMS is kind of like the controller of the battery and making sure the battery is safe. So I would say those are the main major components, and those are the main things that you're going to need to cover off when you're doing an EV conversion.
Okay, cool. I think that gives us a fairly good sort of lay of the land, so to speak, of what goes into it. I'm interested in what level of interchangeability we have with these components. Obviously, we've already talked about the fact you're using the Chevy Volt batteries with a Tesla drive unit. So safe to assume there's some flexibility there in terms of swapping out different batteries. The inverter, as I understand it, is fairly closely tied to the specific electric motor. Is that correct? That sort of has to be mated to the electric motor?
Yes and no. There are some racing inverters out there that are compatible with pretty much any motor, but that inverter needs to be correctly characterized and tuned for that motor. And that process, like most inverter manufacturers, will have a range of motors they already support. But then if you want to custom characterize a motor, we've done that once before. It's a fair bit of work, and it's not so different than tuning an engine with an ECU, but you need to fully map out the motor and effectively tune it to be as efficient as it can be, make as much power as it can, and not ask too much of the motor to the point where you damage it as well. So it's not so different than setting up an engine. I mean, you're kind of doing similar sort of things with the crank and cam, sort of getting everything calibrated and knowing the positions and making sure there isn't noise and electrical signals that are messing that up. So there's a lot of things that run in parallel when you're characterizing an inverter to a motor, and it's a pretty enjoyable, it's a nice challenge for sure. But for EV conversions, generally people will pick a packaged motor and inverter, which is what we call a drive unit. Often the inverter is attached to the drive unit, so it's all one just big chunk of aluminum that has the gear reduction in it, the motor and the inverter all in one. So that's usually how it goes with EV conversions.
In terms of the other components you talked about, so let's say, for example, the charging solution, so you can actually plug it into your home power supply and charge it. Is that again something that's basically interchangeable, these from different models, or would you try and find, for example, probably most people are going to buy a crashed Tesla, just for one model example. Obviously, then within reason, as long as it hasn't been destroyed in the accident, you've got all of that componentry. So that would be the way you'd go, or you can chop and change.
Yeah, the challenge, it's all CAN. Generally, all these components just communicate over CAN. So it's really just a challenge of knowing the CAN, the DBC for that, which is basically the understanding the signals you need to send and receive for that component to be able to control it. If you're using an OEM component, that information is not obviously publicly available. So in the aftermarket, for the easier to access things like the charged and the DC-DC converters, it's nicer to just buy an aftermarket one where you know exactly how to interface with it. And it's a little bit less of that, okay, we have a signal here. We think if we send this signal, it'll charge. Like that, there's less of that going on. So I prefer the drive unit to buy an aftermarket one is extremely expensive, Yes. But to buy a charger or a DC-DC converter is not so bad. So I prefer to buy aftermarket ones that have a DBC and they're easy to interface with, relatively speaking.
So unless you're prepared to dive pretty deep into some reverse engineering of CAN messages, stick to the aftermarket and make your life a whole lot easier is really the outcome there.
Yeah, but there are guys now, like certain components that they're understood, and those specific components you can plug in and they'll be fine if you can. So, I don't want to say only the aftermarket stuff. I mean, the guys in the EV conversions, I have to say, are generally speaking, they're well versed in CAN. They're really willing to put in a ton of work, a ton of time into getting these things working. So, and they share it openly as well, a lot of them. So it's a little bit of a different community, and it's pretty cool how smart some of those guys are.
I think it's probably just worth mentioning that there's never really too much black and white in terms of what you can and can't do. And That really goes for just about anything with modifying cars. And likewise, as you've just mentioned, that never underestimate the intelligence of the aftermarket enthusiast community, and when you get enough of those really smart enthusiasts together, they can come up with some really smart solutions to seemingly insurmountable problems pretty quickly. And then, yeah, as you say, it's open source. Often a lot of these people will quite happily share what they've found. So yeah, as time goes by, access to that information obviously just gets easier and easier as well. Now, moving on, I guess one of the common things that will be on the mind of people who have come from an internal combustion background will be, if I put in this Tesla drive unit or whatever it happens to be, is the potential to, let's say in inverted commas here, tune the electric motor. And you've kind of really addressed this to a degree with what we've talked about with the Evora already, but just to dive a little bit deeper, what I'm meaning here is when we're looking at an internal combustion engine in a factory showroom car, quite often, but not always, there's going to be maybe 10 or 15 or even some instances 20% of power available on the table there. So for us in the aftermarket, sometimes with no hardware modifications, we can unleash that power and that's really usually quite cost effective. Do we have anything similar happening in the electric motor world, or as Tesla provide a vehicle off the showroom floor, that's kind of the limit of what we can get out of it?
Okay, so the main concept I would stress here is that when you have an internal combustion engine, there's that 10 or 15% left on the table because there's a lot of unknowns. And it's a mechanical system that's not perfectly controlled. We're using an audio sensor to determine if the combustion is unstable. Like, it's not 100% foolproof. And you can have the car with one type of fuel here and one altitude and one ambient temperature versus a totally different. So because there's so much variability, there has to be more of a buffer. But with an electric motor, you have so much more knowledge of what's going to happen and control and monitoring of what's going to happen. So the manufacturers can push closer. And then the second point to that is, with electric motors, it's not the power that you make, it's how much power you make for how long. So you can make way more power, but even if you could, then that's just less time, within limits.
Does that go back to your ability to get rid of the heat that we've already discussed, or is there a little bit more to it than that?
Yeah, totally. I mean, well, of course, within limits. Like, if a battery just simply cannot make more power because it'll go below its safe voltage, then that's a limit you can't exceed. But in terms of the motor and the inverter, you could conceivably, if it's able to produce 1,000 amps, you could conceivably do 1,200 amps for a few seconds. It's not going to just, melt. But that's already kind of what some of these manufacturers are doing. I mean, there's one electric vehicle, I'm not going to name names, but I think you press the accelerator at full throttle for 15 seconds and then it just cuts the power. So that manufacturer has basically given you more power than they're comfortable with giving you, but only for 15 seconds. So if you were to tune that and try to ask for that power all the time, well, probably something bad would happen. They've most likely put that limit in there to protect the battery or the motor from either short or long-term damage.
So really what we need to consider is the power versus the time. So is application specific, essentially. What you could get away with for 9 seconds on a drag strip is going to be very different to what you could put out reliably for 15 minutes lapping around a road circuit.
That's the biggest difference with a gas versus electric vehicle. I mean, with internal combustion engines, we're more or less expect that the power that we can get unless the engine overheats, we can get more or less that power for an entire session on the track, or drag racing, it's the same. But with an electric car, the heat that you produce with a little bit more current, you produce a lot more heat. So even just dialing it back by 20 or 30%, you can run for a lot longer. So there's a lot more of just how much do you want. For drag racing, you could make the argument that, yeah, there is a case to say you'd want to be able to modify these things, because for 10 seconds, you probably could get more out of a lot of EVs. But you might do permanent damage to the battery. You probably wouldn't do permanent damage to the inverter or the motor, but depending on the battery chemistry, you could potentially do some damage there. But any other application other than maybe one lap at a short track, you're not really going to gain too much from trying to tune on what the manufacturer gives you in terms of outright power.
Yeah, I think that's all good information for those. It's a bit of a change, I think, of mindset coming from what we're used to, what we're familiar with what we can and can't do with internal combustion. And of course, not everything's going to translate nicely across to EV.
And it sucks. It sucks. It would be nice if you could just, go in there and do some little mechanical change and then be able to unlock a whole bunch more power.
I guess the other sort of element there comes into we're quite used to buying a car that in showroom form produces, let's say, 500 horsepower and it's turbocharged. So happy days, we'll just add an exhaust, a bigger intercooler, maybe change the turbocharger, and all of a sudden our 500 horsepower engine can, with some level of reliability, produce 600 or 700, yes. Or the sky's obviously the limit. So really we need to change our mindset there, because if we're going down the EV path, we really need to firmly decide what our aims are in terms of how much power we want, and then select a drive unit that in production form produces that. Is that sort of a good way of sort of rounding it all up?
Yes. I mean, there's obviously exceptions to that, and the main one being that the way to get free power, quote unquote, is by raising the battery voltage. So if you had X drive unit and you put a custom inverter on, and the base vehicle ran at 400 volts, and now you put a 600 volt battery on there, and you were confident that the windings in the motor could support 600 volts without breaking down, now you can potentially have a different situation and make more power. But this is not using one drive unit supplied by the manufacturer with the same voltage. And if you go and just raise the voltage on a complete drive unit, probably it's going to say, look, this is a higher voltage than I'm allowed to do. So the kind of the exception to the rule of what we're talking about here is, if you can raise the voltage with a higher voltage battery and have an inverter that supports it, or in theory you can hack an inverter and reprogram it to be okay with that higher voltage, then there's a chance to have more performance. Okay. And that's not really available yet. But I mean, in EV conversions, it would be pretty cool if some OEM inverters could be reprogrammed to push the limits a bit in terms of the voltage that they're willing to tolerate before they shut down and say, that's it, I'm scared, turn me off.
Yeah. All right, so I think what we've said, though, probably is going to be applicable to 98% of people doing EV conversions, at least at this point.
Yeah, but my job here is to think about all the guys that are going to be commenting that that's wrong, that's not true.
Yeah.
So I got to try and put an asterisk wherever I can here to protect myself.
Of course, again, the caveat, there's a lot of grey and not a lot of black and white here, but I think you're doing a pretty good job of running us through things so far. Now, just one of the elements that I've talked to you about in the past I want to dive into a bit more is the torque management of an electric vehicle versus internal combustion. And when we're looking at mapping essentially what the driver's requesting with the accelerator pedal versus what the engine's producing, be it internal combustion or electric, really that's what the driver's asking for, is a specific amount of torque, and we're trying to develop that. However, there's a bit of latency, I guess, would be one way of referring to it with internal combustion. It's not a case of we instantly ask for 400 newton meters of torque and we can in a split second get that, but we can with an electric motor. Is that correct?
Yeah, on the custom inverter stuff that I've done, if you program the ramp rate of the torque, like if you program it to be as fast as possible without exaggerating, it makes the sound of a hammer hitting metal.
Okay.
It's an electric current. Nothing is moving, but it is such a sudden change of force that the entire drive unit rings like it's been hit by a hammer. So you are having to dial back the rate at which you ramp the torque, because the tire won't even have a chance to conform to, like, it's just will spin instantly. And it will be very harsh, obviously the drivetrain and the driver. So yes, the bad news is it's almost too easy. Like some of that stuff, what you enjoy with the boost control tuning and the strategy and thinking and how can I map the throttle table and like all those things that were a fun challenge, it's kind of now just put the number you want in, and if the inverter can do it, that's what you're going to get at the end. So it's more about then enjoying making it really quite perfect, so instead the challenge isn't so much to get it to 90%, it's more, okay, it's easy to get to 90%, but like let's really get it to the point where when you're driving it on the track, for example, it's just coming so naturally. You never accidentally put the car into huge oversteer. You're never getting a feeling where the pedal feels like nothing, and then all of a sudden there's too much, and the regen blends in really nicely. So like all of that sort of thing, you can really get a lot of enjoyment out of. But the challenge of developing the torque in the first place isn't there anymore. That part's really easy.
That's the easy bit.
Yep.
I assume that you've just talked about not having big power slides, but a lot of this also comes down to elements of traction control. And again, in an internal combustion engine, traction control actually is a deceptively difficult task because there's so many elements that we can mix in to get a result that we want. And again, short of ignition cuts, which have their own sets of issues, there's sometimes a bit of a lag or latency in terms of trying to dull down the torque that the engine's producing. Whereas, again, I assume we don't have this with electric motors. So does this give us a big advantage in terms of traction control strategies, how effective and powerful those can be?
Yeah, because the inverter is running at 12,000 cycles per second effectively. If it has a good understanding of its speed, which it does, and it has a good understanding of the speed that it wants to be going or the limit, then you can have a lot more control. But it's still challenging. Just like with a gasoline powered engine, I mean, you can cut too much, and the tire just spun because it hit a bump and then it landed, and you're still cutting. So it's not totally night and day, but it is much more powerful.
Okay.
But you still have lots of dynamic situations on a racetrack, right? Where you can, specifically when you hit a bump, you lose traction for a second, and well, really the aim should be a bit higher. Let's let it spin a bit more when we're going in a straight line, and the target should be lower when we're cornering, and we're going 220 kilometers an hour, fully loaded up. We really don't want anything to the rear tires to be spinning at this point. So you have more control for sure. It's less of a challenge, especially compared to a turbocharged car. But if you just said never slip more than 3%, it would feel terrible on a racetrack for sure.
Sure.
Because a tire is not, it's always changing depending on the situation. So you want to allow some slip sometimes, and sometimes you don't want to allow so much slip. So what I'm saying is half of the traction control system is knowing what to ask for, and the other half is getting it. So you still have to know what to ask for.
Yeah, this is sort of a bit outside of what we're talking about right here, but I think it plays in quite nicely to it. I wanted to talk a little bit further on about what the future actually holds in terms of how far we see these cars being able to go. My reference here is the current crop, as the time we're recording this, of Tesla Model S Plaids. They're, I think, if I'm correct here, now the fastest production car in the world on a drag strip. I forget the numbers off my top of my head. I'm sure you can fill in the blank there. My point is that how much more is available in these cars. Basically, we've got these cars now in a production form that you can buy off a showroom floor and drive around with 5 people in them, going not much slower down the drag strip than my purpose-built dedicated drag car was 10 or 12 years ago. That just to me seems absolutely ludicrous. It must be at the point where the tire is essentially a limiting factor, and that sort of comes back to this traction control strategy or launch control strategy. Managing the tire slip almost the whole way down the drag strip. Is there more available, or is it tire technology that's now holding things back?
For sure, in the case of the Plaid, it's on traction control for some period of time. But if you added more power, it would just extend the period of time it was at that 1.1 Gs or whatever it is of acceleration that it can do on those tires. But yeah, absolutely. In terms of drag racing, the EV has so many advantages. It can apply the torque smoothly, that there's no gear shifts to worry about that are upsetting the traction. So it's just a lot. There's almost no vibration. So it's much easier to keep the tire right at that limit. Whereas with a gas car, it's shaking, the turbo's spooling, ignition cuts are happening, and clutches are slipping. Like all of that stuff is hard on the tire and hard to control. Whereas with an EV, it's really just you can pick exactly how you ramp that torque in and how you slowly take it out when there's a bit too much slip. And that's why they're so consistent drag racing, right? You get the same time every single run because it's
almost boring.
It is almost boring in that way.
But you're still running quarter miles in the low flat 9-second vicinity, so it's hard to call that boring.
It's just I understand from a tuner and gas engine tuning perspective that it's frustrating because you spend your life trying to do this thing, and then all of a sudden you see this stupid big 4,800-pound sedan come and do it, and some guy that's never even owned a fast car before goes and does a quarter mile time that's multiple seconds faster than maybe someone that's spent their life trying to do it a low 11, and it's disheartening and frustrating.
But still impressive nonetheless.
It is so impressive. I like to look at motors and how they can make 1,000 horsepower. And you go and you look at like an industrial motor that makes like 20 or 30 horsepower. Like I have on my dyno fan, it's a 30 horsepower motor. And it's like 250 pounds and massive and just clunky. And, it's very impressive that these EV companies have managed to go from, it's a 100 horsepower motor in a car not too long ago was, kind of a challenge and expensive. Maybe in the 80s, a 100 horsepower motor was kind of like, you couldn't just buy that for a couple $1,000s so easily.
Absolutely.
Now these guys have 1,000 horsepower like it's nothing. So the rate of the technology, the way it's ramped up, and how lightweight those drive units are, and they can support that power for extended periods of time is almost mind-boggling to me. Like the rate that technology has ramped up in the last 10 to 15 years. That's actually the most discouraging fact about the aftermarket is like, if you take a Plaid today and you get another 50 or 100 horsepower out of it, it's like, good for you. In 1 year, Tesla's going to have something that has 1,200 horsepower and then 1,500. Like, it's just like you get no time to enjoy your achievement because the rate of technology change is so rapid right now. In the aftermarket, we're used to like the status quo where you can have a Subaru that has 230 whatever horsepower for like, how long has the STI had that much power? Like 10 years. That's just what you get with a Subaru, right? And so it makes sense for the aftermarket to spend a bunch of energy and effort to learn about it, to develop it. But right now, with how rapid things are in the powertrains of EVs from the manufacturers, it's just like, I'm just going to sit back and watch, man.
Hold on to your hat. You're in for a wild ride.
I'm learning and playing with things and this and that, but to make a business case out of, for example, making an upgrade for something that is going to be
obsolete in 6 months' time.
And the next generation. So,
all right, an element that I'm interested to learn a little bit more about, and you've already sort of mentioned as part of that drive unit, you've essentially got some kind of gearing. But this is another area where we're used to internal combustion engines where we need a gearbox to make sure that the engine stays across what is still a very narrow usable rev range as we change the speed that we're driving from stationary to 120 mile an hour or whatever that may be. But that's usually, but not always, not the case with EVs. And again, from my cursory understanding of this, if you look at the sort of torque output from an electric motor, we sort of get peak torque at stall or where the engine's stationary. And then as the electric motor RPM increases at some point, that torque actually starts to fall away. So how do we get away with not needing gearing? Is it just because the usable RPM range of an electric motor is just so massive in comparison to internal combustion?
Yeah, I mean, there's a few reasons. But the best way to boil it down is the benefits of adding a transmission usually don't outweigh the weight and the added friction and all that comes with having a transmission. So that's why, and the cost. That's why most EV manufacturers have just put in a direct, like a single gear reduction. Now that being said, there's a case where you might want a 2-speed because you want to have enough torque from a stop that you can be at the limit of the tires, and then if you do that, by the time you get up to highway speeds, or in the case of like the Porsche Taycan, Autobahn speeds, the motor is now spinning way too fast and it's not operating very efficiently. And so it would make sense to have a second gear. So then you would think, okay, 2-speed transmission. But if you look at the Taycan specifically, it does have fairly poor range. It's not the most efficient. I don't know how much of that is attributed to the transmission. I would assume that it's maybe slightly more efficient at really high speeds, but then it has a loss at lower speeds. And then you look at the Plaid, and then Tesla's just, again, this technology thing I keep talking about. They have a single speed motor that can go from 0 to 200 miles an hour and has almost no loss in power. It has a flat torque up to the 1,000 horsepower, and then the torque drops off, but the power remains constant at 1,000 horsepower all the way up, very little taper, all the way to 200 miles an hour. And I have experience with this. I mean, we can run that car at a very low state of charge on the battery, which usually results in a lot of power loss. And it doesn't matter. At 160 kilometers an hour, it's still making 1,000 horsepower. And on a Model 3, which is only 2 years old, you would have lost from your 450 peak horsepower, you would be at like 320 by that speed. But Tesla just in one step went from huge loss when you have, I was thinking, okay, we need to get longer gears for this drive unit. We should run taller tires, do everything we can to keep it at the higher power, which is at a lower RPM. And then all of a sudden it's like, here's 1,000 horsepower all the time. And don't worry about needing shorter gearing because you're at the limit of the tires all the way up to the peak power anyway. So what do you want?
It's hard to sort of see a real compelling argument for why you're going to need to consistently be exceeding 200 miles an hour. And that is an impressive feat in and of itself. And again, as we've talked about a few times through this, just obviously that evolution as the technology advances, it makes something like a 2-speed gearing seem like a pointless addition of weight and complexity.
The interesting thing to me is that no matter what, if you have a 2-speed gearbox, you have a mechanical system, you have some level of maintenance, you have some level of the, NVH, the customer is going to feel a gear shift happening at some level. And the OEMs can put in so much energy into just developing the inverters and the electronics, because once they figure it out, like that's just a few dollars of chips they need, for example, maybe slightly bigger power drivers than they would have otherwise used, but they save so much compared to not having a transmission. So it looks to me like that's the direction things are going in. There was even a company I was reading about where they'll switch actually the way that the inverter works, so it will effectively be the same as switching gears, because you'll basically go from having quote unquote like a more windings on the motor, so effectively that's the same as having a shorter gear ratio, and then the inverter can switch almost instantly inside to having fewer windings, which is now exactly the same as having longer gears. So
right,
it's crazy to say, but you can actually almost have the gear ratios change in the inverter
without a gearbox.
Without a gearbox. So the point I'm trying to make is, unless you're worried about the mechanical limits, like the bearings and the speed of the motor is spinning, it's hard to see an argument for why a gearbox in the future will be better.
Yeah. I wanted to cover it off because, again, those coming from the internal combustion mindset, a gearbox, we're just ingrained with that. We know that we've got a gearbox. So why do these electric vehicles no longer need one? I think you've really cleared that up for us nicely. Now, we've talked about engine swaps here so far in terms of buying a crashed production electric vehicle and robbing the parts off it. Are there other solutions in terms of aftermarket electric motors, inverters, etc., and batteries for that matter, or are these, at least at the enthusiast level, still just out of reach in terms of cost?
Yeah, I would compare it to buying a specific racing engine from an racing engine manufacturer. Like a prototype LMP2 engine manufacturer. If you went there, you can buy a custom racing engine from them. And how much more expensive is that than buying a road engine and modifying it? It's, in the order of magnitude of 10 times more expensive, power for power. So you can get kind of like a drive unit for $4,000 or $5,000 that has 300 horsepower from a Tesla, or 400 horsepower. If you want the same inverter and motor from the aftermarket at a similar weight, it's about $40,000 or $50,000, give or take.
Okay, that's definitely not looking like a viable solution for probably just about anyone who's following this podcast.
It's going to come down over time, but that's why I was saying before, the things like the chargers, the DC-DC converters, those components where you can buy one from a wrecked Tesla for $500 or something, or $1,000, and then you can get an aftermarket one that is easy to work with for $2,000.
Yeah.
Okay, not so bad.
Sometimes that makes sense, but the order of magnitude there and the specific numbers aren't quite as scary either. Now, I'm interested in talking a little bit about the safety element, which is maybe not the most sexy element of electric vehicles, but as we've sort of seen EVs evolve and start getting involved in motorsport around the world, there's been a few problems that I've seen. One of them, and I don't know if you can speak to this too much, is the governing body's rules around eligibility of EVs and how those integrate with existing internal combustion competition cars. Is the problems there? Is that being dealt with well, or do we still need a few evolutions of those rules? Obviously, these are going to depend on whereabouts in the world you are. I don't have answers for every governing body, but it is something here in New Zealand. We've only just recently kind of got some draft legislation that actually allows EVs to compete.
It's been interesting because in my experience, it's been either people turned a blind eye to it and they're like, yeah, run ahead, go ahead and do whatever you want, I don't care.
That's all good until you win though, right?
Yeah. Or EVs are banned. So, and they are scared of them, and these things catch on fire and everyone's going to die. And no, there's really not that many places that have considered EVs, looked into them, been concerned about it, and then said, okay, this is what we're going to do. That's starting to happen now, but mostly it's just been, yeah, sure, do whatever you want, I don't care, it's a car. Or absolutely, as soon as they look into it, they talk to their insurance company or something, is like, no. And I've talked to a few different grassroots level series, but it's hard for me to be too involved because I've got such a conflict. Anything I tell them is like, well, obviously I'm biased. I'm motivated to tell them that it's going to be safe and fine. So I'm not very involved in that side of it, but my gut instinct is that if an electric car catches on fire, you're not going to put it out. It has to burn until it's done burning. But unless you have a really, really big impact, I haven't seen where the batteries just go up so fast that the driver can't get out of the car. So in terms of the safety for human life, I think it's more safe or equal to an internal combustion vehicle.
Sure.
In terms of being a hassle for a day at the track, if a car catches fire and you can't get it off the track, that is a problem. It'll probably ruin the rest of the day for everybody, in that, you've got this car somewhere that's got to spend a few hours burning. So
I suppose just yellow flag that section and
just
the track
drive around it.
Drive around it, and that's probably okay. I think maybe.
Honestly, I've looked into a few different fires, and I haven't seen one happen at the racetrack yet. It doesn't seem to be that the batteries light on fire from being aggressively discharged. It seems to be that they light on fire while charging, usually because there's some kind of fault in the way the battery management system hasn't observed that there's a problem, or something's gone wrong with one of the cells, and that wasn't handled properly. So that's a really good news. It doesn't seem like thrashing the battery on the racetrack and really taking everything out of it while you're discharging it. That doesn't seem to really be a fire risk. It's either puncturing and really hitting something, which again on a racetrack I haven't seen that happen yet. I mean, we've had customers smashing curbs and just absolutely burying their cars into stuff on the racetrack, and there's never been a battery failure. So that's really encouraging.
Okay, well, I mean, it's still early days, but I think there's probably a bit of a fear around some of these situations. We've seen videos of electric vehicles burning, and as you say, you can't put them out. They just burn until they've consumed all of the fuel available to the fire. So that is definitely off-putting, but nice to hear that that's actually not maybe at least a significant threat on a race application. And as you say, it's not going to instantly turn into a ball of fire. You've got the ability for the driver occupants to vacate the vehicle. The other element, I guess, that goes along with this is we're talking about some very high voltages. Is there a risk of electrocution, and what kind of mitigating factors can we put around that?
Yeah, it's an interesting one. I mean, I haven't been shocked before, which is like good.
Typically.
So we have an isolation module in both the Lotus and the 350Z, and I don't know how common this is with general EV swaps, but I wouldn't do an EV swap without one. But basically what these modules do is they monitor the resistance between the positive of the high voltage system and chassis ground, and the negative of the high voltage system and chassis ground. So they can warn you if the isolation is breaking down. And then you can use that as part of the control system to open. Remember how I said there's a power distribution system with big switches called contactors? Those can open those switches. So if that isolation breakdown was occurring outside of the battery, say it was at the motor or at some cabling going to the charger, for example, then that would solve that. And if it's still at the battery, like let's say, for example, the battery was punctured and something was connecting, somehow the battery cable to chassis ground, then at least you could be warned on the dash to say, hey, like the isolation is low, there's a shock risk. On our 350Z hybrid, we actually have high voltage lights similar to what you see in Formula One that indicate, whether the high voltage system is active or not. And then it also will flash like a really bright, painfully bright red and yellow at a really high frequency to indicate that the isolation has broken down or is unavailable. In other words, don't touch the car.
So there's a bit of education that would go around that for the likes of track marshals?
The crew specifically. Track marshals. We did one day where we kind of explained to track marshals, but I think until there's a standard, I think the reality is kind of like you tell the track marshals, look, like I'm kind of on my own here. So if something happens, don't pull me out,
Yeah.
I mean, in my car, we have the high voltage gloves right beside me. So, there's options too on how you can be have a bit of ideas, so at least if something's going wrong, I can put the high voltage gloves on and open the door and get out of there. So I don't know. The problem is I haven't had that terrible experience yet to know exactly what happens when it goes wrong. All I can know is from a couple of the things I've seen in Formula One where some mechanics will get a shock when something goes wrong. And I haven't seen it be like terribly fatal, or like shouldn't say fatal. It's never been fatal that I've seen. It's just been, I don't think there's been any permanent injuries. So that's really encouraging, but it's definitely something we need to understand better and deal with. And there should be like a standard, like this is the light, this is a system. It has to flash like this when this is occurring. If you're going to run an EV, you have to have this equipment available, near your tow hook or something that someone can put on high voltage gloves and pull you out of the car. Just an example like that. There should be some standard of how to deal with a potential shock hazard. That's, I think, more important than the fire thing, actually.
Yeah, that makes sense. And again, as the adoption of EVs in competition becomes more mainstream, clearly I think the governing bodies are going to have to adopt some of these standard practices as well. And maybe as we're recording this, it's still a little bit too early for that to have happened, but no doubt it will come in time. Now, you just mentioned your 350Z, and I did want to talk about this because you've got quite a unique, albeit maybe complex strategy in that where you've got an internal combustion engine and you've also integrated kind of a KERS style electric motor as well. Can you give us sort of a 30,000 foot view of that car briefly? Sort of what are the components involved in it and how do those integrate?
Yeah, sure. That's kind of been a really interesting project because it's combined we talked about the torque control and how the challenges that you kind of lose when the electric's a bit too easy. So it's kept everything really difficult with having a gasoline engine that's naturally aspirated and really, peaky and angry and, just kind of hard to control with an electric system. So we've gotten rid of the flywheel, the starter, basically everything in the bell housing, and we've replaced that with an electric motor. And that motor is directly coupled to the engine all the time. And so the motor acts as a starter to start the engine. And when you want to start driving, the electric motor starts driving and also spinning the gas engine. And the electric motor has to speed the car up enough in first gear to the point where the engine can fire. So it has to get up above 500 RPM or whatever before the engine fires. And the reason we did that was I was just getting really anal with weight. I said I don't want to have clutch hydraulics. I don't want to have flywheel. I don't want to have a starter. I don't want to have a clutch where we have to disconnect. And why do we have all that stuff? It's a race car. As long as it can start moving, it's good enough. It's got a sequential gearbox, so I don't need to disconnect it.
There's a little bit more in terms of advantages with having this electric motor there rather than just getting rid of your weight of your flywheel and clutch and being able to start the engine though, correct?
Oh, yes. Sorry. Yeah. So that's just how it works. The purpose of it is to have more power and just be a fun challenge. So we wanted 200 horsepower. The first iteration, we got 100 horsepower. And then we rewound the motor to be able to work better at high RPM. And now it's about 140 horsepower. And we're now looking to make a different battery at higher voltage to try and get closer. But it's been a really cool project. The whole system is really nicely integrated. So it just does some really, really cool things, the way that the power blends in and out and the regen and the engine braking and the different maps. And that was kind of the goal of the project, was just to learn and just nerd out on it and do stuff that you would imagine are being done in really high levels of motorsport and just kind of learn about it and experiment. And yeah, it's been a really, really cool project.
I think that the fastest way to expand your own knowledge is to dive in boots and all like you have there and kind of figure it out, because the theory is good to a degree, but at some point you've actually got to see how that theory matches reality. So I totally get that side of things. Now, you mentioned saving weight. I am interested, by the time you've added batteries and the electric motor, how does that offset? Where do you sort of end up in terms of overall weight compared to what you had prior to going down that path, even though you've got obviously an extra 140 horsepower on tap?
Yeah. So my goal was kind of like my really, really overly optimistic goal was 1 pound and 1 horsepower. So we ended up short on power and higher on weight. So I think we added 250 pounds and we got 140 horsepower. So not quite there. But I mean, we went to Mo Sport and the car was well over a second and a half faster. So the weight wasn't as much of a penalty as the gain in power, which was a bonus because the goal was, just to at least not lose lap time with 250 pounds on a time attack car with it's dependent on downforce is kind of a lot. So
definitely, yeah.
But that's why the starter, the flywheel, the clutch, all those pieces, like that was 60 pounds or so that we got back.
Yeah. Let's talk a little bit about how you're integrating the power from the internal combustion engine with the electric motor, because I mean, I'm guessing on face value, you could have this pretty crude and rudimentary whereby you essentially push a button and it's almost like a nitrous kit, giving you another 140 horsepower, which I mean gets the job done, but certainly isn't that nice, isn't that easy to control as well, particularly on corner exit. If you sort of instantly bump up 140 horsepower, that's probably not going to end too well. So I'm guessing you went with something a little bit more advanced than that.
Yeah, I actually was had a competition Scion FRS that I was driving for a team that slapped on 150 shot of nitrous to this 200 horsepower Scion FRS. And we were in a drifting competition, and it had the nitrous on the switch on the gas pedal. And I lifted off just 10%, and I lost that nitrous, and I just tank slapped into the wall and hit the wall so hard because I lost all of my power. So yeah, trust me, that wasn't going to happen. It's really cool. I spent a lot of time on the dyno. The first thing I did is I totally characterized the naturally aspirated engine to get the torque output. So when I command a certain torque, I get that out of the engine. So first I fully mapped the gas engine to get the torque that I wanted. And I basically mapped the pedal to be more or less 0 to 80% of the pedal goes from 0 to full output of the gas engine. And then as you ramp the gas or the accelerator pedal further from 80 to 100, the electric motor would add on to the gas engine, which was already at full power. And, I swept it. Basically, it's a torque request table like we were talking about before. And it's very beautiful. Can't tell when the electric motor is coming on. Then on a second stage to that, I then started adding a way to use the gasoline engine to charge the battery. So for example, if I wanted 60% power of the engine, I would instead take 80% power from the engine, and then 20% of that power I will take from the motor as regen to charge the battery. So there's all these different modes on the steering wheel that you can pick that affect how much of that partial throttle charging do you want to occur, because that will cause the battery and the motor to overheat faster. So it's a compromise between, do you want to keep the battery charged up higher and keep it from dropping, or do you want to keep the system from overheating? So I've got like endurance modes where it'll focus more on charging but run the motor at a lower power. And then there's modes that are time attack, for example, where it's not going to bother trying to charge. It's just going to try and not overheat. So it'll just run the battery down, but not over. So there's all these different modes that are like quite nice, and they smoothly integrate with the pedal. And then they're also ramped in with lateral G-forces and whatnot, so that I basically looked at data from the year before and I said, okay, when am I not at 100% throttle? Like what cornering G-force and speed can I not get to 100% throttle because I'm traction limited at that cornering? And so I used that as my base to kind of make sure I'm not asking for I'm not wasting the battery in the electric motor, just doing that and then cutting it with traction control. So it's a bit of a feed forward table for the motor, and it worked really, really nicely because I was able to just plant the gas pedal in these very high speed, high commitment corners at Mosport and not have to worry like, oh, do I have to tippy toe into it and hope the traction control catches it. It just ramped it in really nicely. So it was really pleasing to drive the car and feel that working.
Yeah, I mean, it sounds like a complex system that would be very satisfying when it all works as, or even maybe better than anticipated. In terms of maybe reality versus what you had initially thought when you planned all of this out, did you sort of go and build all of these strategies, test them at the track, and find that actually you needed to rethink your entire strategy, or were you pretty much on the ballpark straight out the gate?
So we did everything on the dyno. I tested everything on the dyno, but then when we went to the racetrack, it was just good. It was just like
perfect. One
of those situations where, well, first of all, when you're running that car, there's so much going on that like 95%, if it's at 95%, I'm looking at something else. There's something else that's not at 95%. But I looked through the data, and I especially went to Mosport, and I was just like, man, like it was just so good that it was almost disappointing. I wanted to tune on that a bit, but that's just part of that is just because, it's still only 630 odd horsepower at the wheels, and with the downforce and grip we have, it can
make it a bit easier.
It can put most of it down, unless you're at 2 Gs of cornering, you can put most of it down. So it wasn't a huge problem. The main problem we had is there's a big vibration that we're still struggling with. And it's most likely partially due to that there's just not enough inertia in the flywheel, which is the rotor of the motor. And we had the shaft breaking. Like there was a lot of mechanical problems that we had with just the interface between the engine and the motor. And so that's kind of been frustrating and a dumb problems that we shouldn't be having.
But the control strategy was good straight from the start.
I know. I guess the electronics guy got the electronics right, but he couldn't figure out the mechanics. So there you go.
All right, look, been really interesting getting this insight so far, Sasha. However, it's time to move towards wrapping this chat up, and we always finish our podcast with the same 3 questions we ask all of our guests. The first of those is, what's next and in the future for you? You've already seen a very significant change in your direction with your business or businesses. What do you sort of see in the future?
Yeah, well, I think we kind of talked about it a bit today. I mean, our business Mountain Pass is growing all the time, and the next thing is kind of like, do we build a fully electric road racing car? Because I think it would be really cool at some point to try and do something where we can do a 10 or 15-minute sprint series and compete with gas-powered cars. That would be fun. And I miss doing wheel-to-wheel racing. It's been a while since I've been doing wheel-to-wheel. You know how it is. You build a car and you get that thrill when you're really going after someone and running too wide through some sections where you probably shouldn't be. So maybe something like this would be in the next couple of years, I would hope. And then, of course, the Z, and we have some new bodywork for it, which is really exciting. It's like a kind of a JGTC GT500 thing. So yeah, lots going on, just always difficult to prioritize because you can only do so much. So we'll see.
Naturally. particularly with a lack of a huge amount of other people being involved in helping you out, correct?
Yeah, but we have some great guys here, so we can make a good bit of progress. We just can't do everything, so we have to pick.
Okay, next question. Given what you've learned so far through your career, everything you've experienced, if you were to give advice to a younger version of yourself to help sort of maybe avoid some pitfalls, fast track your sort of progress through your career, what would that advice be?
I have to use an example where we gave some advice to a guy at PRI. I think we were at the Optimum G seminar or something, and he came up to us and said, I want to get into racing. It's so hard. How do I do? Blah, blah, blah. I can't get in. I said, man, like, if you just keep going and volunteering and putting yourself out there, just volunteer for free at some race teams, while at the same time you're learning and, not just being useless, but you read great books, you watch HPA Academy videos, gold member and all that. If you really learn that stuff, you'll be ahead of 80% of people in knowledge. Then you just have to get the experience. There's so many guys that they go to the engineering school and they have no experience, and it's just like, go get the experience and have the knowledge, and it will take care of itself. I promise you. There's such a demand for people that are talented, that have the practical skills and enough knowledge to not be dangerous. It will not be hard.
100%. I think that is always the challenge, is getting that mix of the knowledge and the real world practical experience. And you can have all of the knowledge and none of the experience is not actually that useful. So at some point you do need to transition your skills over and actually get out there in the real world. But your point is really, really important there to note that wherever you are in the world, wherever you're listening to this, there are race teams out there, or whatever you're into, workshops for that matter, who are crying out for good quality help. Smart people who are self-starters, who are prepared to put in some hard yards. And as you say, maybe to start with, for free, volunteering. And I can guarantee you the return on your investment there is going to pay dividends if you're really devoted to pursuing a career path. So really, really worthwhile advice for those listening to take on.
That guy that we spoke to there at PRI, he is now like a senior engineer at an IndyCar race team.
Wow. Well, there you go.
So it didn't take him long. It took him maybe 4 or 5 years, and he's right up there. So he had no connections. He knew nobody. And he just volunteered, learned the stuff, went to the seminars, got the hands-on experience, and, didn't have a big ego, I'm assuming, and was, could work with people. And there's such a demand for good, hardworking people right now that it is not hard if you are that. If you're having trouble, you're probably not that hardworking. That's probably the problem.
Right, we'll move on to the last question for today, Sasha. And if people want to follow you, see what you're up to and what you're doing, where are they best to do that? You got some social media we can link to?
Yeah, so the my personal Instagram is Sasha Anis #14, and then the Mountain Pass Performance Instagram is also has all of our EV related stuff going on. Those are the main ones I would say to check out.
Hard to believe there's already 13 Sasha Anis that managed to beat you to it.
I know, right?
Always disappointing. All right, well, we'll link to all of those in the show notes anyway.
Thanks, I appreciate
so it's
that.
nice and easy for people to find. All right, Sasha, it's been great chatting. Thanks for all of your input here today. Sort of hopefully expanding on the knowledge that people listening have now on what the EV world actually involves and what's involved in maybe considering electric electric motor swap into a conventional car. So yeah, thanks again, Sasha. Really appreciate it.
Yeah, well, thanks so much. And I apologize if everything we spoke about with EVs was a little bit not so exciting with me basically being Debbie Downer here. But I will say that when it comes to EV conversions, one of the main challenges right now, specifically for us, is having shops out there, having companies that can offer that as a service, because no one knows how to do it. So it's very challenging to make a product for that. If anyone wants to do it, I'm going to have to basically coach them through every single step of it. So, if you're in an area, I think, where there's a demand for that, an interest for that, and you're a good salesman and you can convince someone to spend $60,000 or $80,000 on an EV conversion because it's really cool, that in 5 or 10 years, you'll probably be a leader in your segment. So ultimately, what I'm saying is it's an investment. It is a long-term thing right now. It was for me, obviously, a big investment and a big risk to take. But I think if there's more people that can competently do good EV swaps, that will actually spur the development of the products that will make the EV swaps easier to do. So it's kind of a little bit of the chicken or the egg thing.
Yeah. It's sort of one has to come to drive a market to be filled. So yeah, I see exactly what you're saying. I mean, it's safe to say that time is coming, though. I don't think it's too far away. So it's exciting for sure. And I can't wait to see where this market goes to over the next 5 or so years.
Totally, me too. I mean, who knows, man? With the Plaid, like once drive units like that are available to guys for $10,000, like
unbelievable.
You're not going to be able to beat that with a internal combustion engine. How much do you need to spend to make 1,000 horsepower? I don't know. Significant, right? So,
well, I mean, it's not only that, which is something we haven't really even touched on today so far. It is, obviously, if we want to make 1,000 horsepower with an internal combustion engine, the reliability of that package to a big extent is going to come down to the base engine that we're starting with. But I mean, even if you're sort of talking twin turbo LS, which at 1,000 horsepower would be relatively unstressed, I would wager that a Tesla Plaid drive unit is going to be long-term much more reliable than your twin-turbo LS. And maybe there's some people who will disagree with me there, but this is my podcast and I said it.
No, I think you're 100% right. So it's like I'm saying, if you're doing these EV conversions, eventually you get into this rhythm where you've got this formula and you keep repeating it. Conceivably, once you've got everything down, you're not going to have upset customers with blown engines. So that's a plus. Or maybe it's a downside
100%.
Because it's less recurring revenue. I don't know. It depends how you look at it, I guess.
No one really likes blown engines, but that is a very significant consideration there as well. When you're buying these production drive units with X power output, and that obviously the safety systems that we've talked about, if you operate it within those realms, it is going to be long term very reliable, and that's a significant consideration for sure. All right, I think we'll leave it there, Sasha. Anyway, thanks again for your time. We really appreciate it.
It was great talking to you, man.
If you enjoyed this episode of Tuned In with Sasha, we'd love it if you could drop us a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get bigger and better guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt anywhere in the world. This is a great place to ask any questions you might have too. I'll do my best to answer them if your review gets picked. So this week, a big shout out to Syrup710, who's said, "So glad I subscribed. Your posts and podcasts are great to snack on." I really appreciate the comment there, Syrup710. We don't necessarily recommend eating these podcasts, but however you're consuming them, we're glad that you're getting some value out of them. And on that note, for those who are only following us on the podcast so far, make sure you check out our other social media. In particular, we're on Facebook and Instagram, HPA 101. Anyway, thanks for that comment, Syrup710. Get in touch with your size and shipping details, and we'll fire off a fresh tea straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpaacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.